minute. Okay, good afternoon. Okay, yesterday we just start to learn the collection of rigid bodies, and we introduced the concept of moment inertia, right? That's very important. How to calculate the mass moment inertia, and also you need to know the parallel axis theorem because most time you can just refer to the textbook to find out the mass moment inertia for simple geometries, but we need to calculate the mass moment inertia about any axis sometimes, right? Because we know that the mass moment inertia is not only depend on the mass distribution, so but also depend on the axis you are talking about, right? We need to specify which axis you are calculating the mass moment inertia. Just like if you want to know the moment, you need to specify the point or the axis you are calculating, right? So that's for mass moment inertia. And then we just introduced the concept of the collect diagram, right? We just have just like we have this uh, FBD. FBD is the wheel force system acting to the rigid body, and we also have the KD. KD is actually inertial force and inertial moment, or we call kinetic moment. Okay, inertial moment is equal to Ig alpha. Ig is actually the mass moment inertia about the mass center. Alpha is the angular acceleration of the rigid body. Mag is actually the inertial force to represent the resistance to translation, right? And because is actually a vector, so we just often apply its projection in x direction, in y direction, and sometimes in anti-coordinate system. So we will have the following three scalar equations. Because for kinetic moment or the moment of the force system in the wheel force system, the the moment is actually always perpendicular to the plane, because we only talk about the general plane motion. General plane motion including translation, rotation, and general plane motion. Okay, so here for the moment or the kinetic moment, they just became a scalar actually in the axis. Okay, so we have two scalar equations of the equation of motion. We have one moment equation, and just as we said, actually we can regard these two force systems are equivalent force system. I mean, the real force system from based on the FBD, and the inertial force system based on the KD. So, because they are equivalent, that means the resultant force of the two force systems should be equal with each other. That's why we have sigma F equal to mag. And in x direction, we will have the x component of the resultant force for the real force system will equal to the x component of the inertial force. Similarly, the y component of the force system, the wheel force system, will equal to the y component of the inertial force. Since they are equivalent force system, not only the resultant force, should be equal with each other, also the moment about any point should also be equal to each other. So that's why here, if we choose the point to be the mass center, we choose the point to be the mass center, because this one is quite important, okay? So if we choose the point to be the mass center, we will have sigma mg equal to Ig alpha. Sigma mg, what's sigma mg? Mg is actually the moment, is the moment of all the forces about the point G. Yeah, you should calculate this. Use FBD, the real force, not only the forces but also the moment. Okay, and this is the sigma mg you calculate based on FBD, and KD will be the inertial moment about G, because here when we calculate, from KD, actually the inertial force um, have been simplified to locate at G, okay? And so when we calculate the moment about the mass center of the inertial force system, the inertial force, because passing through the mass center, so it will have no moment about the point G, so it will equal to Ig alpha, because we know that moment about any point will equal to each other, equal to itself. So if sometimes we prefer to another point, just an actual point P, and again, these are two equivalent force system. So the moment about point P of the real force system will equal to the moment of the inertial force system about point P. When you calculate the moment about point P of the whole of the real force system, you just do that based on what you have learned in statics, right? And here is the moment about point P of the inertial force system. Just same way here about point P, not only Ig alpha will remain here, right? Because we know that moment about any point will be equal to itself. So Ig alpha, but here you also need to pay attention that not only the inertial moment have produced the moment upon point P, also the inertial force will also result in moment about point P. Okay, so this one, these three equations actually apply to the rigid body which is doing general plane motion. Specifically, if the rigid body is translating, we will have corresponding three equations. This is again the resultant force should be equal to each other. This one, if we choose the mass center to calculate the moment for the two force system, I mean the wheel force system, the inertial force system, this one is we call FBD, right? This one we call KD, and we will have sigma mg equal to 0 because the Ig alpha, because if the rigid body is translating alpha equal to 0, okay? But sometimes maybe we can choose an arbitrary point, just like A point A. So for the two force system, they are equivalent. So again, the moment about point A of the real force system will equal to the moment about point A of the inertial force system. And here, even Ig alpha equal to 0, but never forget the inertial force will have a moment about point A. And again, when you calculate the inertial moment by the inertial force, still equal to the moment arm of the inertial force times the magnitude of the inertial force. Okay, again, we define counterclockwise as positive, clockwise as negative. Okay, so sometimes maybe it's better to use anti coordinate system, and it's similar except instead in x y uh, direction we use normal and tangential direction. Okay, so this is the example we didn't finish yesterday, so we just uh, figure out together today. Uh, this crate rests on horizontal surface and the kinetic friction coefficient is given. We need to find the acceleration of the crate. As we know that the crate may slide, right? When we push it, the crate may slide. Also, sometimes the crate may tip over. It happens. And according to our experience, to tip over actually is easier, right? It's not so just will save your energy. I mean, okay. So we don't know if it will slide or tip over. This time we need to assume, we need to make assumption. Um, okay, so here the note, when you push the crate will either to slide or to tip over. So here you can just assume the crate to slide, and then we can check this assumption. So how can we check assumption whether it's slide or it will tip over? So let's say the FBD for the crate is weight, and this is the acting force. And then for the ground, it will have the normal um, supporting force, will have the friction force. Okay, so the normal force here should be very careful. Actually, it should be distributed node, right? Just like the friction force is actually also a distributed node. And then this is just the distribution, the resultant force of this distributed force. Okay. And so when you are in high school, and generally, if you draw FBD, you would like to draw like this way. It's a weight, it's a normal force. No, actually, the normal force doesn't necessarily pass through the mass center. Okay. And most time it does not pass through the mass center. So it will have the distance x to the mass center. I mean, the two parallel forces, the perpendicular distance from these parallel forces, I mean the weight, and the normal force will be x. If if you calculate this, you found out that the x is smaller than 0.5 meter. That means the normal force is inside the range. Okay, so that means for sure that the crate is sliding. Okay, because here when it's slide, we have the kinetic friction force. Well, you could choose 0.2 times the NC. But if x greater than the 0.5 meter, because here 0.5 meter is half of the size, that means it's impossible. That means uh, the the crate is actually tip over. So I want to know whether maybe you can tell me if the crate is tip over, what does that mean? If the crate is tip over, it will tip over about point A, right? If tip over about point A, that means the normal force should pass through, because normal force is contact force, right? We know that the restrict here for the surface force, they are contact force, no contact, no force. So if it tip over, that means just like here, right? This is tip over. Sorry for my drawing. So the normal force should be here. This will be the normal force, right? And this will be the friction force, okay? So here, anyhow, we assume that it's sliding. And so if it's sliding, that means the crate is translating. Since it's doing translation, so we can apply the equations of motions again in x direction. The x component of the resultant force of the wheel force system. So here, this is FBD. The KD is quite simple. Okay, the KD is quite simple because we have MAG, because we only have inertial force IG alpha equal to 0. So we have sigma Fx equal to the x component of the inertial force, MAGX. Here is AG itself. So we have this equation. And again, in y component, we will have NC minus the weight equal to 0. Here, you need to be very careful that here you have NC, you have AG. Okay, here you can calculate. Here you can calculate NC, right? And so you can calculate AG, but we need to check the X. We need to check the X, whether the X in middle school, because you don't need to make assumption, because in middle school it was told that the crate is sliding. That's why it's very easy for you. You only need to list the two equations, the two scalar equations, that's enough. But here, right now we know that the crate may also tip over, so we should check out whether it really is sliding or not. Okay, so here we can just calculate the moment about mass center. Again, as I said, because this FBD and KD, they are two equivalent force system. So for two equivalent force system, not only the resultant force should be equal with each other, also the resultant moment about any point should be equal with each other. Here, we just you can calculate G point. Sure, not you can just maybe you can calculate the moment about point A. It's okay. But because I calculate the moment about the G, the inertial force will have zero moment. So it will be much easier. That's why I list here. Okay. But you can also calculate the moment about the point A. It will result in the same solutions. So sigma mg for the wheel force system, we calculate based on the FBD. So for the weight, have no moment because it passed through the mass center. For P, its moment arm will be 0.3. And because under the action of the P, it will have tendency to rotate about G clockwise. That's why we have minus here. Okay, so we also, for NC, the normal force, it will produce the moment about point G also. And this is the magnitude of NC. This is moment arm for the NC. Don't forget, we also have the friction force here. The friction force also has the moment about point G. Okay, this will be the moment arm and also the tendency to rotate about point G clockwise. That's why it's minus here. Okay, so equal to 0. And then we calculate the value of x. So found that x is really smaller than 0.meter. Um, so so yes, it's really sliding. Okay, here, since the value of x, or I mean the distance from NC to the mass center is smaller than 0.1 meter, that means NC is normal, is within the range of its bottom. So the crate slides as originally assumed. If x was greater than 0.1 meter, the problem, you should rework the problem because it will tip over. Okay, you can try that, or maybe you can calculate. So the minimum value of P that the crate will start to tip over. You can calculate the value. We say, because that's in statics, we generally can do that, right? So at which value at which value of P the crate will start to tip over, and at which value of P the crate will start to slide. Okay, you can compare them. Okay, so here a two-bond disc is attached to a uniform six-bond rod AB with a frictionless corner at B. If the disc rolls without slipping, yeah, this one is very important. Select the correct FBD. The disc is attached to a uniform six-bond rod AB. This is AB. This is a disc. And here is a frictionless corner. Frictionless, that means there will be no friction force. So for MB, 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 they are the same, right? There's no friction force, okay? And so weight, but here is 8 bond, is 6 bond, 6 bond. Which one? Definitely should be 6 bond, right? For the rod, right? Here, you should be very careful. The weight just penetrates my center. So here the rod is giving, right? So this one is wrong because only from this we know that it's not correct. So we can say for this AC, the difference is the weight. They are same, right? And NA and NA and FS. The only difference is FS. So here, the disc rolls without slipping. So the friction force here, so should be in which way? If the disc rolls without slipping, oh, you see? So this corner, the velocity should be downward. And then for this one should be downward, right? So which one? Can you tell me which one? This velocity. And so this will be the contact point, right? This one will be the contact. Can you tell me the omega? V equal to omega R, right? So this one will be the omega. So for the disk A, it will rotate. It will rotate counterclockwise, right? It will rotate counterclockwise. Am I right? It will rotate counterclockwise because this will be the IC, right? Instantaneous center of zero velocity, right? IC. And so accordingly, the omega should be counterclockwise, right? And then accordingly, from this, we can analyze the disk. We can analyze the disk separately. So for the disk, we'll weight and NA, and and here for the rod, F and the Fs. So this is omega. You see, accordingly, only the friction force will provide the moment to rotate, right? So we will know we will have sigma m equal to Ig alpha, right? And sigma m is provided by the friction force. Ig is the mass momentary inertia about the mass center of the disk. Alpha will be the angular acceleration. Okay, so C, answer C. Okay, C. The answer should be C. Okay, no sleeping. Result is no sleeping. So actually here the friction force, because we know friction force is actually resist the tendency to move. Here, the tendency to move, and move is to move to the left. So this is Fs. Or you can use the just now we have the equation of motion. So the answer should be C. Okay, you're right. The answer should be C. But if the disk rolls with sleeping, select the correct FBD. Here, with sleeping, this one or this one, with sleeping. Also say why. With sleeping, because it moves downward, and also because with sleeping should be forward, right? And so yes, because it will resist the tendency to move forward. So answer should be also C. But different here. Here is a resistance force. Here is a resistance force. But here is not resistance force. It's actually say just like provided the moment to rotate. Okay. As the linkage rotates, box A undergoes, I think we have done this before, general plane motion, pure rotation, linear translation, collinear translation. Which one? The link have the same length, rotates, and so A will undergoes, and try to choose the answer. And try to choose the answer. Which one? I think we have done this before. Yeah, thank you very much. You are really very good. D, yeah, not maybe. You should be sure about yourself. They are doing collinear translation. Why? Because they are always parallel to its original position. So because here they have the same length, okay? So that's why they will just do collinear translation. The number of independent scalar equations of motion that can be applied to box A is number of independent scalar equations of motion that can be applied to box A is 1, 2, 3, 4. Which one? Yeah, just we have talked about it. Scalar equation, we only have 2. Or we have 3. Collinear, just for, we can just draw FBD, right? FBD for the block, weight, normal, right? If there is friction force, and for A For A here should be AN, okay? MAN, and MAT, right? Yes, we only have two independent scalar equations here. Okay, we only have two independent scalar equations here. Okay, why? Because here if you take sigma mg equal to 0, I mean, about the mass center, it will result in the same with the scalar equation of magx oragt. Okay, so please do this by yourself, and then just do this 10 minutes, and then upload, and then we will continue the study. A uniform collecting rod BC has a mass of 3 kg. The crank is rotating at a constant angular velocity is given. Please find the vertical forces on rod BC at points B and C when theta equal to 0 and 90 degrees. Here, AB is rotating, and you see BC, here BC is doing what? Because here the radius of the disk is also 200 millimeter. So actually BC is translating also, right? BC is translating. So AB is rotating, the disk is rotating, BC is translating. We need to find the vertical forces on what BC. At points B and C, can you try to do this and then upload online? 10 minutes.